Welcome to AP Physics Made Easy. My name is Eric Sampson, and what I want to do is help you get a 5 on your AP Physics test. Now listen, AP Physics is a notoriously difficult class with a very low, in fact, the lowest pass rate. But if you watch my videos and pay attention to what I'm saying, I think I can help you a lot and probably get you a 5 on your AP test in May. So let's go ahead and get started on today's lesson. It's about distance versus displacement, speed versus velocity. These are concepts that people who are new to physics have a hard time untangling. So let me see what I can do for you here. All right, so let's start with distance and displacement. So let's say I have a person here standing in position A, and the person walks to the maybe 10 meters to the right and ends up in position B and goes, wait a second, this isn't where I'm supposed to be. So the person then walks 30 meters to the left, ends up at position C, which is where they really wanted to be. Okay, well now what I can do is this. I can talk about the distance the person traveled, or I can talk about the displacement of the person. They're related but not the same. So distance is a scalar quantity, and it's basically just how far the object traveled. So the person walked 10 meters here and 30 meters here. So basically what I have is a scalar quantity that's irrespective, is blind to direction, has no idea which way. And so in this example here, the person walked 10 meters and the person walked 30 meters. And since I don't consider the direction, I end up getting a sum of 40. The person walked 40 meters. And this is something we're used to thinking about in our day-to-day lives. Like if I walk this way and then I walk that way, I don't care about the direction. I just care about how tired my legs are, how far did I walk. But now let's talk about displacement. So this is something quite different and far more important in AP Physics. We don't really use distance much in AP Physics, but we sure do use displacement a lot. So the symbol for displacement, you're going to see so much this year, is delta x. Now, just so you know, delta is this triangle. It means delta is the way we read it. It always means change in. And mathematically, it is always the final value minus the initial value. So for this person, I would take their final position minus their initial position. That is their change in position, and that is what their displacement is. It is a vector quantity, so direction matters. So in this case here, the person ended up 20 meters to the left of where they started. So I'm going to use negative to indicate leftness. Okay. So in this case here, how far away is the person from their starting position? Well, they were displaced 20 meters to the left, which is the negative direction. And one way I have of thinking about displacement to think about, I started in this place, I ended up in that place. I know it's silly, but that's just one way I have of helping me remember. Now let's talk about the difference between speed and velocity. So similarly, one is a vector quantity and one is a scalar quantity. Now, in this case here, if I want to talk about this, since both speed and velocities are the rate at which we move through space, we're going to have to give the time. So I'm going to say, let's just say this entire journey took 8 seconds. All right, so let's talk about the average speed of the person. So speed is a scalar quantity. It doesn't matter what the direction is. And so I'm going to use this equation. The average speed of the person, because the person obviously stopped and then went around, so they weren't always going the same speed. So I'm going to talk about the average speed. I'm just going to take the total distance the person traveled and divide it by the total time it took the person to make the journey. So in this case, the average speed equation, I'm just going to substitute in the distance they traveled, which was 40 meters. The time it took was 8 seconds, and 40 divided by 8 gives me 5 meters per second. On average, that's how fast this person was moving. That was their speed. All right, now speed is irrespective of direction. It is a scalar quantity. Now let's try it this time, but let's talk about the average velocity. So the velocity cares about distance. So the equation for average velocity, instead of distance over time, it's displacement over time. And remember, displacement is a vector quantity. I started in this place, I ended up in that place. And so I'm worried about this, not the whole journey. So I start with this equation. I'm going to substitute in for delta x. We remember from a previous example that was negative 20 meters because he ended up moving 20 meters to the left between his two positions. It still took 8 seconds, so I'm going to divide by 8. And in this case here, I'm getting a very different value than what I got with the speed. I'm getting negative 2.5 meters per second is the average velocity of the person. Even though some of the time they're moving in the positive direction, on average, their velocity was negative 2.5 meters per second. Now notice that they're both measured in meters per second, but one is a scalar and one is a vector. So they do both have the same units, and you got to be careful not to let that confuse you. Well, now let's talk about the difference between average velocity and instantaneous velocity. All right, so let's just say I'm sitting in a car at a red light, so I'm going 0 meters per second. Now the light turns green. At time t equals 1 second, I'm going 5 meters per second. I'm speeding up, right? We'll talk about that in the next lesson. And then say at t equals 3 seconds, I'm going 15 meters per second. But then the light ahead is red, so I stop. And so at t equals 4 seconds, I'm back to going 0. So that was the motion that occurred. Hopefully you think my cars are pretty cool. I sure think they're cool, okay? Well, now let's just talk about this here, okay? So the total distance traveled, let's say, is 20 meters is how far these cars went, or this car went. So what was the average velocity? Well, in this case, the average velocity, I'd say we went a total of, we started in this place, we ended up in that place. That was 20 meters. It took 4 seconds, so our average velocity is 5 meters per second. Right? But here's the thing. Most of the time that car wasn't actually going 5. If you looked at the speedometer throughout this trip, there was probably 2 moments along the trip where it said 5 meters per second. The rest of the time it said something different. So the instantaneous velocity, which is much more important in physics, is a measure of how fast and which way the object is going at any given instant in time. So let's just look at it here, okay? So at t equals 1 second, this car is going 5 meters per second in the positive direction. And at t equals 3, this car is going 15 meters per second in the positive direction. Now, because the magnitude of the instantaneous velocity is the same as that for the instantaneous speed, we often end up using the word speed to refer to the magnitude of the velocity. Right? So I'll say the car has a speed of this, but it's indicated in the problem which way it's going. So I'm just saying that sometimes we tend to use speed to just indicate the magnitude of the velocity. Okay, so let's look at this problem here. So what I've got is this. I've got 4 different segments here, and here's what they represent. A bug flies 4 different directions, shown by different colored arrows. And the important thing in understanding this problem is that each of these segments took 2 seconds to complete. So the total trip is 2 plus 2 plus 2 is 8 seconds, okay? So what we're going to do is we're going to determine the instantaneous speed for each of these segments, and then we're going to determine the average speed of the entire journey. Well, let's go get on it, okay? Here we go. All right, so let's start with the instantaneous speeds. So this one here, each of these lines represents 1 meter, and I see I have 8 lines, so that's 8 meters. Remember, it took 2 seconds, so I have 4 meters per second is the instantaneous speed here. We're assuming that in each of these things, the bug is traveling at a constant speed. So, well, what's the instantaneous speed here? Well, what I have here is that 6 meters. So the instantaneous speed is going to be 6 divided by 2. That's 3. And I'm going to do the same thing for the next one. That's 10 meters, so that's 5. And the next one is 4 meters, so that's 2. Those are instantaneous speeds in each case. We're assuming that that it was traveling at constant speed on each of these segments. Now let's talk about the average speed of this entire journey. Well, what I'm going to do is I'm going to say average speed is the total distance traveled divided by the total time. So I take the total distance here. I believe that works out to be, 28 meters. It took 8 seconds because it's 2 plus 2 plus 2. And that means the average speed works out to be 3.5 meters per second was the average speed of this bug. Well, let's do it, but now let's work with vectors. Let's talk about the instantaneous velocity, which is a vector, and the magnitude of the average velocity. We're not going to do the direction. We could, but we're not going to. So let's just go ahead and try this here. Ready? Okay, so this first one is going to be 4 meters per second. We've already established that this is 8 meters and that this took 2 seconds. So the average speed here is 4 meters per second in the positive direction. This is also the positive direction. And so in this case here, we're going to get 3 meters per second because it traveled, its displacement was 6 meters in the positive direction and divided by 2 seconds. But look here, it traveled negative 10 meters. So 10 meters in the negative direction. So what I'm going to get here is negative 5 because it's a vector. And here I'm also traveling 4 meters in the negative direction divided by 2 seconds. That's going to give me negative 2 meters per second. So those are my instantaneous velocities, which are basically the same in magnitude as the speeds. But in this case here, I have negative values for these, indicating that the displacement and therefore velocity is in the negative direction. Now, if I want to find the average velocity, I'm going to have to use the tip to tail method because that's how I add vectors. So I'm going to start where I started and end where I ended. So the length of this vector is the magnitude of my average velocity. So to do that, I'm going to find the x and y component. So the x component I can see is 2 meters. And I can see that the y component I'm sorry, this is negative 2 meters, my bad. And this is going to be positive 2 meters. All right. So if I want to find out what the magnitude of this is, I'm just going to use Pythagoras. So I'm going to say the resultant square is equal to the square root of each of these values squared. But notice what happens when I square this, the negative part disappears, and I end up with 2.8 meters. As always, thanks for watching. If you like this video, remember, like this video. Consider leaving me a comment. If there's some video you'd like me to make, I'd be happy to do that, or maybe you could just give me some feedback on how to improve. You might want to check the description below to see if there's some links I've included that could help you out. And of course, as always, I would really appreciate it if you would like and subscribe.